How do you understand complex transistor biasing techniques? Imagine trying to keep a delicate balance in a busy marketplace. That's what complex transistor biasing is like. It's about setting the right conditions so transistors work smoothly, no matter what changes happen around them. Transistor biasing is the process of fixing a transistor's direct current operating point, also called the Q point. This point determines how the transistor amplifies signals or switches on and off. Getting this right is key for reliable circuit performance. Let's start with the basics. A bipolar junction transistor, or BJT, needs about 0.7 volts between its base and emitter to turn on if it's made of silicon. This voltage is called the base emitter voltage. Biasing makes sure this voltage and the current flowing through the transistor stay steady, even when no input signal is present. One simple method is fixed bias, where a resistor connects from the power supply to the base. The resistor controls the base current. But this method isn't very stable because the transistor's current gain, called beta, can vary a lot between devices and with temperature changes. Another approach is collector feedback bias. Here, a resistor connects from the collector to the base. When the collector current increases, it causes a voltage drop across the resistor. This reduces the base current, helping to stabilize the collector current. It's a bit smarter because it provides some automatic correction. Adding an emitter resistor is another common technique. This resistor is placed in the emitter leg of the transistor. It develops a voltage proportional to the emitter current. This voltage acts as negative feedback, automatically adjusting the base current to keep the collector current steady. It's like a built-in stabilizer. The most popular method is voltage divider bias. Two resistors from a voltage divider that supplies a stable voltage to the base. This setup keeps the base voltage steady regardless of variations in the transistor's beta. When combined with an emitter resistor, it offers excellent stability and allows the circuit to handle larger signals without distortion. Understanding how these methods work together is essential. For example, combining voltage divider bias with an emitter resistor creates a very stable operating point. This setup is widely used in amplifiers because it maintains a consistent Q point, even if the transistor's gain or temperature changes. The main goal of complex biasing is to keep the collector current and the collector-emitter voltage stable. This stability ensures the transistor works reliably in different conditions. Negative feedback from the emitter resistor helps automatically adjust the base current, preventing the circuit from drifting. Load line analysis is a useful tool here. It shows how the circuit's resistors and supply voltage define the possible operating points. The intersection of the load line with the transistor's characteristic curves gives the actual Q point. Setting this point around the middle of the load line allows maximum undistorted output swing. In practical terms, engineers use these biasing techniques to design circuits that perform consistently. Whether in audio amplifiers, radio receivers, or embedded systems, stable biasing means signals stay clear and circuits last longer. In summary, understanding complex transistor biasing involves knowing the different methods, how they stabilize the operating point, and how feedback mechanisms improve circuit stability. This knowledge helps in designing reliable, high-performance analog electronics that work well under varying conditions.